I'm pleased to present RMFER, Semi-Supervised Contrastive Learning for Facial Expression Recognition, with Reaction Mashup Videos. This study enhances facial expression recognition, key for human-computer interaction, and effective computing. RMFER combines labeled and unlabeled data, notably using reaction mashup videos for training. In this presentation, we'll cover the key challenges, technical insights, and breakthroughs of our approach. Machines in FER are increasingly adept at discerning emotions, significantly influencing fields from human-computer interaction to psychology. Deep learning like CNN, especially for managing occlusions and varying lighting, has propelled these advancements. Another key development is the adoption of vision transformers, concentrating on specific facial regions rather than the entire face, for a more refined understanding of expressions. While FER has advanced, a major challenge remains the lack of large-scale datasets. Facial expressions are inherently complex and ambiguous, varying across individuals and cultures, making accurate labeling and categorization difficult. Our work addresses these challenges by using methods to collect and utilize unlabeled facial expression data, the RM set. In our research, we've made several key contributions to the field. Firstly, we've developed RM set, an extremely large-scale unlabeled dataset, tailored for semi-supervised contrastive learning in FER. To our knowledge, this is the first unlabeled dataset of its scale in this domain. Our second major contribution is the introduction of RMFER, and semi-supervised contrastive learning framework. RMFER can leverage inter-sample attention for contrastive learning. This framework effectively utilizes RM set. Furthermore, we've conducted extensive evaluations of RMFER. Our results show that it achieves state-of-the-art performance across 3 distinct datasets. We also employed MDS plots to illustrate how RMFER leads to improved feature distribution, thereby enhancing the accuracy and reliability of facial expression recognition. To tackle the challenge of data scarcity in FER, we explored the use of unlabeled data, focusing on reaction mashup videos. These videos, featuring multiple individuals reacting to the same content, provide a rich and diverse set of facial expressions. This approach allows us to capture a wide range of spontaneous reactions, triggered by the video. Our approach is based on 2 key assumptions regarding reaction mashup videos. First, since these videos compile individuals' reactions to the same trigger video, we assume that multiple people watching the video simultaneously will exhibit similar facial expressions at specific moments. Second, given the rapid changes in the trigger video content, we assume that facial expressions at different times will differ significantly. These assumptions are fundamental to our method of utilizing these videos for enhancing FER. While our methodology leverages key assumptions about RM videos, we've observed that these are not always consistent. For instance, in a snapshot from one such video, while many individuals displayed surprise, others did not. This illustrates the first limitation: not all viewers react similarly at the same moment. Furthermore, our second assumption, that facial expressions will differ at temporally separated points, also doesn't always hold true. These inconsistencies highlight the need for additional supervision in our approach. To refine our assumption, we implemented additional supervision by filtering the positive and negative sets, based on their attention to the anchor. The criterion is the inter-sample attention to facial expressions, which can be quantified by our attention module. This figure illustrates the attention between the anchor and positive samples, and between the anchor and negative samples. With the training by inter-sample attention loss, the model learns to increase attention between similar expressions, and decrease it between dissimilar ones. This learning process enables us to effectively filter the positive and negative samples, using inter-sample attention. By conducting contrastive learning with these filtered sets, our model achieves improved performance and more distinct attention differentiation. Let's take a moment to review the process of transforming reaction mashup videos into our RM set, a crucial step for our framework. We start by removing the trigger film area from the reaction mashup video. This area doesn't contribute to the people reactions and is therefore excluded. Next, we extract each face from the video, categorizing them based on the specific video they are reacting to, the timing of the reaction, and the identity of the person. This categorization involves assigning a face ID to each face, enabling us to track each face consistently throughout the video. As the position of each face remains relatively stable in reaction mashup videos, it can be possible to track the face ID by the position. Finally, we address the issue of distorted face ratios. Since reaction mashup videos often combine several videos, the width-to-height ratio of faces may be altered, potentially impacting FER performance. To counter this, we correct the face ratios, ensuring the integrity and quality of the data for our framework. Next, we'll outline our framework and its loss function. Our framework comprises 3 main components: a classification, an attention, and a contrastive module. The learning process begins with pre-training inter-sample attention, excluding the contrastive module, for several epochs. Then, we train the entire model, including the contrastive module. Training involves FER loss, IAL loss, and ACL loss, culminating in the development of the feature extractor. We'll discuss each module and stage in more detail later. Let's begin with the classification module. This module uses a standard CNN model to process face, images, and classify facial expressions. The CNN backbone, denoted as FFET, acts as the feature extractor. It extracts features from the input images, which are then passed through FFER, a fully connected classifier layer, to generate the predicted value, white hat. For this module, we employ cross-entropy loss, referred to as LFER. Next, let's explore the attention module, which is designed to learn inter-sample attention. The input and output formats mirror those of the classification module, but there's a key difference: it trains inter-sample attention. Among batch features, the process begins with the feature vector f passing through the projection head H, transforming into vectors E. We then create a Casine similarity matrix, S, by measuring the Casine similarities between all projected features in the batch. S undergoes a process we call self-masking softmax to transform into the inter-sample attention matrix A, where each row sums to 1. Importantly, we adjust the diagonal values of it to be close to 0, to avoid self-referencing. The attention matrix A is then matrix multiplied with the feature vector F to form the attentional feature vector V. This vector is processed through the classifier FIAL, and the module is trained through cross-entropy loss LIAL. IAL means inter-sample attention learning. A key aspect here is how each Aij in the attention matrix A signifies the extent to which feature Vi references feature Fj. To ensure that AI doesn't become disproportionately large, we adjust diagonal values close to 0. This is what we term self-masking softmax. During the pre-training epochs, we focus on training only the classification and attention modules. This phase lays the groundwork for the initial inter-sample attention, which is crucial for subsequent contrastive learning. Moving on to the contrastive module, it takes 3 sets as input: anchor, positives, and negatives from the RM set. This module employs attention-based sampling to improve the positive and negative sets, leading to more effective contrastive learning with these enhanced sets. It's crucial to train the attention module prior to the contrastive module, as inter-sample attention plays a key role in the sampling process. In the positive set P, samples that exhibit high attention towards the anchor are selected based on a gamma ratio. Similarly, for the negative set N, samples with low attention to the anchor are chosen using the same ratio. The contrastive learning is conducted with these carefully sampled positives and negatives. We've adapted the N-event loss to accommodate multiple positives. Given the reliance on inter-sample attention, we've named this approach ACL, which stands for attention-based contrastive learning. In the testing phase, inference is conducted solely through the trained feature extractor and the classification module. This means that our M set, the attention module, and the contrastive module are not involved in this stage. Essentially, this approach ensures that no extra computations or data are needed during the inference step. We evaluated our methodology using two metrics: overall accuracy and average accuracy on 3 datasets: AffectNet, RAFDB, and FER+. The overall accuracy is the proportion of the sample with the correct answer out of the total sample. Overall accuracy reflects more the accuracy of classes with more samples in the test set. The average accuracy is the mean of the diagonals of the confusion matrix. It shows the average performance by expression category. Average accuracy reflects the accuracy of a class equally, regardless of the number of samples per class in the test set. We've conducted a comprehensive quantitative comparison against all state-of-the-art methods published to date. Our model's performance was evaluated in 3 configurations: training only the classification module, training up to the attention module, and training all modules, including the contrastive module. Notably, the performance of our model without ACL surpasses that of the baseline model, indicating the positive impact of training inter-sample attention, even without contrastive learning. Moreover, our fully trained model, incorporating all modules, achieves SOTA performance across almost all metrics and datasets, with the exception of overall accuracy in FER+, which is attributed to the class imbalance in the FER+ test set. Additionally, our framework utilizes semi-supervised learning. We aligned our experiments with the same settings used in semi-supervised methods. The results, displayed in the top right table, show the overall accuracy using only 4,000 labeled samples from RAFDB. Here, our model also outperforms other semi-supervised learning models. This figure illustrates the attention values between anchors and positives, as well as anchors and negatives. In our model without ACL and RAL, the distinction in attention values between positives and negatives is relatively subtle. However, as training progresses with the IAL loss and the ACL loss, a clear trend emerges: attention towards positives increases, while attention towards negatives decreases. The figure on the left displays the MDS plot for the AffectNet validation set, comparing our baseline model with the full model. This plot is generated based on the Casine distances between each sample. In our model without ACL and IAL, there's a noticeable intermixing of different classes. However, in the full model, the distinction between classes becomes much more pronounced, with each class appearing more cohesive. To quantify this observation, refer to the table on the right. It shows the average distance between the class center and its samples. Notably, in most classes, the model trained with contrastive learning demonstrates the shortest distances, indicating more compact and well-defined class clusters. Thank you all for your attention and engagement during this presentation. It has been a privilege to share our work on RMFER, semi-supervised contrastive learning for facial expression recognition, with reaction, mashup, video with you.